Okay, so hello everybody. The project is the DCoMEX project, data-driven computation mechanics at Exascale. I am the coordinating person of this. It is a RIA research and innovation action in the framework of Euro High Performance Computing joint venture, which is family, let's say, of people within the European community that are all around the high-performance computing topics, and everything is built around the new generation of machines that are now present and developing. These are pre-exascale machines and almost exascale machines at the moment. Just a second. It is a quite small project in terms of participants, so it's we feel like it is a little bit a family project. So it is NTUA and our group, which is M group, and then it is ETH, and from ETH it is the CS lab, the lab of Petros when he was in ETH before going to Harvard, and also it's CSES from ETH, and then it's the University of Cyprus and the Department of Mechanical Engineering there, which is in close collaboration with the medical school. And they provide us with the use case that you will see later concerning cancer immunotherapy treatment. And then we have TUM and GRNet, which is the local HPC provider. TUM and Bjorn Bencher there, who also moved from TUM to Zurich, and he's actually doing the pre and post processing development and provides with the corresponding tools in the DCoMEX framework. Now, the goal is to fuse machine learning and data-driven inference models, as well as large-scale linear algebra solvers, to solve extremely demanding computational mechanics problems, like the ones that you will see later. And of course, deliver an integrated open source, user-friendly, and customizable computational mechanics framework that harnesses the capabilities of next-generation European exascale machines. Now, the overview of the platform is the core, which is the MSolve computational mechanics multiphysics solver. It is an open source software that is developed completely in-house in National Technical University of Athens. It is the test bed for our simulation and our numerical demonstrations. And this basic engine, simulation engine, is orchestrated by Corelli. So Corelli is on top of MSolve, orchestrates the data in order to perform a forward and inverse uncertainty quantification, and distributes all the processes in the machines, in the processors, so that all operations can be made efficiently parallel. At the moment, this integration has been prototyped and developed in Pittsdaint. We have tested the core integration in in both examples that we are developing, as you will see later. And we are at the process of integrating the framework to other machines as well, not only Lumi, but several machines in Europe. Namely, we will go for the machine that is in Luxembourg. I don't remember the name. Here you will see the orchestration. We have the Corelli as the work scheduler, which according to the needs of the inverse and forward UQ analysis, it provides the necessary data distributed to the workers, and the data is processed by the MSolve engine in collaboration with Green. This Green is a very essential part of the proposal. It is a so-called AI Solve library, which is an integration of linear algebra solvers, which are high-performance computing oriented and also AI enhanced. I will make some description of AI Solve later on. And then this process returns the values to the Corelli for further processing and optimization or uncertainty quantification or compute likelihoods or whatever. And more or less here is the same pipeline analyzed in modules. These are essentially the work package processes of the project. Not many things to say here. Applications. We have two demonstrators, let's say, two test cases that we should prove what we are saying. The first one is a large-scale biomechanical cancer tumor system. And the aim is to enhance the efficacy of treatment and optimize patient-specific immunotherapeutic strategies. So, in this process, we have patient imaging data. We process the data and create corresponding models. The models are then solved from our simulators. Uncertainty quantification takes place, and then after we develop the models in the high-performance computing environments and enhance the whole procedure with AI techniques and especially surrogates, because these are very extremely computationally intensive problems, we can proceed to optimization of therapeutic treatments and clustering tumor-specific markers based on predicted responses. The second test case is a material design test case. So we have advanced materials which may have inclusions or additives in more than one scales. Essentially, these could be 2 or even more, or 3 or 4 scales. If we're talking about, for example, nano-reinforced concrete materials, and the process, the aim here is to design structure material specific property. That is to say, we have to design the structure and the material at the same time simultaneously and get the result that covers all phases from the lower scale to the real scale of the structure. Now, a few words about the surrogate modeling strategy. We initially explored the diffusion maps category of dimensionality reduction, manifold learning, let's say, approaches, and however, we abandoned it because even though it can be efficient, it is very problematic in the sense that it requires extremely well fine-tuning of the parameters, and which is extremely problem specific as well. So it creates a lot of difficulties. So we switched to convolutional autoencoders. So we are always talking about parameterized problems like UQ or optimization problems. So we always have a set of parameters, thetas, the theta I is here. And as the initial, let's say, offline phase, we generate samples of response parameters based on these theta, the intrinsic, let's say, parametric quantities of the problem. This could be the design variables, for example. Then we condense the output, the response space to the latent space, a lower dimensional space, through an encoder, and then also we develop a decoder, and then establish a relation using a feed-forward neural network between the parametric space and the latent space. So this is the strategy. The way to perform our calculations is that from the parametric space, instead of going directly to the solution phase through a detailed and expensive time history finite element analysis, for example, we bypass this through going to the latent space, to the encoded space, through this fast-forward neural network, through these relations that we have established from our data sets, and then use a decoder to go to the solution space. So this is the whole strategy. We have demonstrated this in many examples. I will show you briefly one. It is a multi-story building subjected to a random earthquake. We have a number of random parameters. The analysis is a nonlinear analysis, including both material and geometric nonlinearities. Using the autoencoder, we can produce very, very accurate results with errors of less than 4%, 4-5% in all cases, even in the extreme values here. And just give me a second. Sorry about that. And you can see here the benefit, the cost benefit, which is extremely pronounced in cases we need to perform a large number of parametric analysis. For example, if we have 200,000 Monte Carlo simulations, the reduction is from 68 days to 5 hours, but this is only in simple laptop 7-core laptop result. However, still we can see the reduction that can be achieved. Now, going to very intensive applications like the material design, for example, if, for example, we have a material design in several scales, where in each Gauss point we need to perform a sub-finite element analysis and even go lower and lower, then even if we train neural networks to solve the problems for replacing the constitutive matrix, for example, this is a scheme for that we implement, that especially when we are talking about concrete, reinforced concrete materials. We have let me just use the lighter here. No, it's the spotlight. I'm trying to use the.
It's okay, we see the annotation with hands.
Okay, I'll do this with the annotation. So here we have the large scale structure, the building, for example, and at each Gauss point where we have to realize the constitutive relation, we have to solve a sub-problem of representative volume elements with the aggregates in of large dimension. Then we should go deeper, and at each Gauss point of this RVE, we should assign another Gauss point with the aggregates of the very fine dimensions. This is clearly a scale separation in the concrete, because here we made talk of aggregates that could be in the order of a few centimeters. And here of aggregates of sand, let's say type, that can be of the order of micros. And then we can even go deeper at the nanoscale if we reinforce the paste with carbon nanotubes, for example, or graphenes. In order this analysis to be tractable in FE into the nth scheme, let's say, we definitely need to replace the constitutive relation with some surrogates. And this is an hierarchy of deep neural networks that has to be built, starting from the lower scale, going to the next, and then to the next, and then construct the total DNN that has inside all the information of the past scales and passes this information to the last structure. Even if you want to do that and replace this analysis with the neural networks, the training phase is still intractable, because as you will see, no. Sorry about that. How can I get rid of these?
I cannot see what you're viewing, but
Go back to the thing that you used in order to on the whiteboard tools.
Yeah.
And clear maybe there.
No, and then on the whiteboard tools, if you click there,
okay,
you will find an eraser.
Yes, great, thank you.
Okay.
And then I will go back here. Okay, even if we want to use a surrogate, we need to have something like 5,000 model evaluations for training at each level of hierarchy. This creates by itself a computationally demanding problem in order to create the data set. And this definitely needs the synergy of high-performance computing, even for the surrogate model approximation. So, when we're talking about large-scale applications, we always nowadays think that the synergy of surrogate and machine learning, let's say, methodologies with high-performance computing is absolutely necessary. So, in this framework, DCoMEX has developed, essentially, we are prototyping this library, the so-called AI solve ecosystem. This is an ecosystem of high-performance computing methods solving the linear equation systems that the basis of these methods are iterative solvers. These iterative solvers are supported by AI-enhanced domain decomposition and algebraic multigrid methods. In order to, and they are accelerated this way. And therefore, this combination is then deployed in the high-performance computing environments. And we have a lot of things to take care of, like energy awareness. We have to optimize the communication and essentially develop efficiently this library in modern exascale architectures. You can always interrupt me and ask questions if you want.
I would suggest we keep them for the end.
Okay.
So we have a block of the presentation.
This is an example of how this AI solve performs. We have a coupled bio problem, which is coupled structural and porous media problem. It is a parametric problem which involves unsettled parameters. It is a relatively large example, but not that large because we needed that for testing. It has only 40,000 degrees of freedom. And here you can see the performance, both in terms of acceleration in CPU time, as well as in number of iterations of the proposed iterative solver. So what we do is that we use the surrogate, the convolutional autoencoder, to get the initial estimate of the iterative procedure, which is a PCG-based procedure, a precondition conjugate graduate method, essentially. So we use the surrogate model to get the initial guess, and then we refine it through CG iterations based on some kind of methodology. Here, for example, you can see the CG iterations based on algebraic multigrid. And we go for a further step forward. Go ahead. Sorry, just give me a second. Now, we have implemented a POD improvement of the AMG solver, which essentially utilizes the same data set we used for constructing the convolutional autoencoder, but also in order to produce the AMG transitions from the high resolution to the lower resolution. I don't have a representative scheme here for this, but I can show it later if someone wants to go in further detail of how to use the POD to enhance the algebraic multigrid procedure. So taking advantage essentially of the surrogate, we can first of all, we can increase the fidelity of the surrogate model at the desired level. So we can start, for example, from an accuracy of 10 to the -3 or 10 to the -2, depends on how well we treat the surrogate model and how well we inform it. But then we can perform the iterations and get the desired accuracy at any desired level of degree that we want. And here you can see the tremendous gain we have in CPU time if we are seeking for large accuracies of the orders of 10 to the -9, -8 with respect to classical iterative solvers, like the AMG solver that is there before our improvements. And you can also see that in the iterations, we have a significant reduction. And then again, you can see the same comparisons with other iterative solvers, with ILU and Jacobi preconditioners. And again, you can see very good behavior of our solver, even if we use advanced preconditioners. So I think that this AI solve essentially put us a step forward with respect to the state of the art in solving large-scale parameterized problems, as I told you. Then the application that we are working at is the one that you saw of the one of the concrete. We have a number of parameters that are random, all stemming from the material nonlinearity. These are parameters that have to do with the dilation, the cohesion, the hardening parameters, stuff like that. We can see here that we have very good predictions of the surrogates with respect to actual calculations of the detailed models, and even though these predictions can be further improved with the AI solve strategy. And also we can use this to optimize the structure and optimize, for example, the direction of the reinforcement at each point. At the moment, we are deploying this framework. We call it DCoMEX material framework, in combination with Corali framework for further testing and deploying it to the Exascale machines. We are at the process of prototyping it. We have not yet get the true speed up we want, because we are at the process of deploying it in Pitstein and other machines available. Now, the second is the cancer tumor growth model. I will go briefly on this. Essentially, this is a toy model of the cancer. Not a toy model. It is an idealized, let's say, model of the tumor growth. You can see here. Is it spotlight? Okay. This is 1/4 of the model because of the symmetry conditions. Here is a tumor. You will see a zoom later on, which is surrounded by the tissue, which is a normal tissue, let's say. And the question is that the tumor has a set of parameters that control its evolution. Our colleagues from Cyprus have developed this mathematical biological model of this tumor growth modeling, which can contain a system of up to 15 or 20 differential equations, partial differential equations that are fully coupled. So if I go next. So see here, for example, you can see the tumor and how it grows in time, and this growth depends on a series of parameters that are all coupled together. For example, the interstitial fluid pressure, which influences and vice versa the oxygen concentration and create a pressure environment that interacts with the tumor. Here, these are all equations that are describe the evolution of these parameters as well. So at the bottom, we solve a couple problem between the structural model and the fluid model. We are talking about essentially a porous media kind of fluid problem, because we are talking about very, very small velocities here. So we have the Darcy conditions. And at the moment we have, and this is essentially the source dependent on the fluid vascular pressure difference. So this is a diffusion equation that fully interacts with the structural model and vice versa. So here are the pressures that are stemming from the solution of this porous media problem. And this is a system of equations that can be interdependent with other equations as well. However, for the moment, we have tested all standalone equations as they are in order to validate them solve with COMSOL. We have fully validated the forward problem, the one-way coupling from the solid to the fluid. For example, you see here that we have exact matching between MSOLVE and COMSOL. This is a coupled problem. We solve it with a staggered integrator, with a staggered and not a fully connected, let's say, solution scheme. And here are also the pressures for the one-way coupling. Now we go to the inverse way coupling from the fluid, from the structural to the fluid. Okay, and here again we have absolute coherence, and we coincide exactly with the COMSOL. And finally, we have the fully coupled problem. So it is both ways coupling in this staggered scheme, as I told you. And we get exactly the same. What you see here is a displacement of the of one node of the mesh as a function of time. So it's a time evolution of the displacement. So we have finished essentially the validation phase of the multi-physics formulation, and now we are in the process with Sergey and Sebastian to include this forward uncertainty quantification problem for a third step. We have also deployed. We are also in the process of deploying this integration to Pittstain, and looking forward to get this communication for the forward UQ problem, then the inverse UQ problem, and then finally include all equations, which is something like 10 equations here that has to be solved simultaneously. Train our surrogates and use AI solve in order to go to the optimization step. So this will hopefully and gradually lead us to our final result with respect to this bio application as well. Here also you see the results of the pressure in time, console versus MSolve. So I think that we have essentially developed MSolve at the level that could perform this multi-physics analysis, and we are ready to use it. So here is our website for the project for anyone who wants to visit it and go through some results and papers that are there. I think that's all. Thank you for your attention. Ready to hear your questions.